In this first exercise of chapter 10, we're going to see how to price the options, and we're going to be using the Black-Scholes Merton price. So here we have the price, this would be the date, this is the interest rate, these are the dividends, and here we have the date to maturity of the options, the expiration of the options, if they're puts, and further down you're going to see the calls, strike price, and these two fields we're not gonna use them. And here we have the implied volatility. So I give you all that, and then with that you're gonna compute the D and the cumulative probability of D and phi D, and then this is gonna give you the price. Now in this price specifically, you're gonna get the put price. Now I'm gonna transform everything into call prices. So you see that for puts you have here the call price, and this one you do it with the put call parity, and then for calls, then these two prices are going to be the same, the one for the price and the one for the call price. Right, now we're going to assume then that we have one position, and this is basically going to conclude the solution for workshop 10 exercise. For question 2, we're going to add two variables. So those two variables are going to be related to, or two parameters actually, they're going to be related to the volatility, the skewness, and the kurtosis. So in here you're going to have the Gram-Charlier formula. This Gram-Charlier formula is going to be much bigger than what we had before. And remember, the Gram-Charlier formula is for call option prices. So if you see this Gram-Charlier formula, it's going to depend on this volatility, the skewness parameter, and the kurtosis parameter. So then once you set all the Gram-Charlier formulas for all the options, so at the beginning you're going to have certain values. So I'm going to actually copy paste my values here to the right so that we see how they change. And let's put this initial option prices. Here volatility is very low because we're considering that the volatility is daily. So here paste. Alright. So then you see that as so here you see that the Gram-Charlier formulas are actually changing. So if I put here, I don't know, crazy volatility 0.5, you see that here the errors change. So now the error, what is it going to be? So you have the Gram-Charlier price, you have the call option price, and this is the market price that we computed in question 1. And here you have the error, which is basically the square difference of these two things. So the square difference of these two things is going to give you the mean squared error. Now the whole idea is that we're going to minimize the sum of all these errors. And here I've kind of cheated. To make the error bigger, I've multiplied it by 100. So now after I use solver to get this mean squared error, the idea is I'm going to get these parameters, and these are going to be the optimal parameters that actually minimize the mean squared error. So for some options we do a really good job, like for these ones, but then you see that the ones that have a very low price, I mean, no matter what, the error is going to be very small. So I mean, this is not fair with these options to compare them with these ones, but anyways, that's the way it is. And this concludes question number 2. Question number 3, it's gonna repeat exactly the same thing with the same model with the Gram-Charlier, but now we're going to include kurtosis. So you see that the mean squared error in this case decreases from, so it's 173 when we include kurtosis, and we only had the skewness, it was 196. So including kurtosis actually makes us improve the fitting of our model. In question 4 and 5, what we're going to do is we're going to use the Black-Scholes option price model, and we're going to have this implied volatility, So these are going to be the implied volatilities we have. And the whole point is to fit in a regression with some other parameters. So on the left hand side of the equation, the y, it's going to be the implied volatility. And then we're going to regress that against this set of values. So the first one is the moneyness, here moneyness squared, then the time to maturity squared, and the cross product between moneyness and time to maturity. So in here, the only thing we're going to do, which is very easy, is we're going to run a regression. So this is the regression, and then this regression depends on, so it's 09063, so it's going to be this column that is going to be regressed against the one that starts from P up to T. Alright, so we regress against all these parameters, we find some values, and then based on these values, we're going to have what I call here a fitted volatility. Now you see the fitted volatility is not exactly the same one that the implied volatility, given that we're fitting a linear model with quadratic terms. So these are pretty close, it's not exactly the same, but now given this fitted volatilities, I can recompute a Black-Scholes price. So I compute the D, the phi D, and so on, and then I get my model-free implied volatility price. So the original price here was 10 cents. Now the price given my new volatility is going to be 6 cents. Or another case here, it's 124, and I compare that with the 167. All right. So you're going to have some errors, which is normal, given that this is just a model. Now from here, we're going to move into, we're going to use this fitted volatilities as starting values. And now what we're going to do is, these initial values are the ones that we used, or we got actually, from, let's see here, from this regression. So these are the values that we got from the linear regression. So those are going to be my initial values. Okay, so these are the ones I have here. And now the question is, okay, how do we get the ones I haven't taken the second part? So this is actually not really difficult. So I have my fitted volatilities. So these fitted volatilities are going to depend on this NLF estimates. So when I start, I'm going to start with, let me copy paste this here. So I'm going to start with these values here. These are going to be my initial parameters. So now you see that my fitted volatilities are going to be the same ones than the ones I had in here, in this column. The column EU and the column AG are now the same. So then I'm going to compute with this model my market price. So sorry, my implied volatility function price, and then I originally had my market price. So given those two, I'm going to have an error. So this is the error here, and then with that error in mind, I'm going to compute in this case the average error. So the error is the square difference between the implied volatility function price and the market price, well, which is L9, which is the same thing. And then, so I'm going to do this cool thing where I'm going to minimize this mean squared error by modifying these values here. So right now my mean squared error is, let's say, 0.023. My guess is if I put these values in here, it's going to be lower, right? So this is after I run solver. So here you have to run solver and modify by changing these parameters. So you see that these are two different things. So the first one is a linear regression. The second one is using solver so that I minimize an error. If you're curious, here I have percent error. So you can also do the same thing, but now instead of doing a regular error, you do a percent error, so that you take into account the level of the price. And the third one is going to be a Q-like function that you can also use to minimize, so that by changing these parameters. The last exercise I'm going to solve here is the option pricing with the GARCH, question 7. So the first thing you have to do is create variables to calibrate. So these are lambda, omega, alpha, and beta, and then you have the starting values. So this is what I'm going to do in this Q7 price, and here I have the inputs. So lambda, all my parameters. Now the next thing I'm going to do is, it says, well, you have to generate 50,000 scenarios, and then it says data maturity equals 50. Why 50? Because I have two sets of options, ones that expire in 18 days and the other ones that expire in 50 days. So I'm going to create here this number of variables is going to be 50, and the number of random variables is going to be 1000. So that's 1000 scenarios, and then I have one random number for every single day. The third thing I'm going to do is I'm going to have a model for my volatility. So here what you have to think is, well, you have some initial volatility, which is going to be this 0.0004, and then you're going to have a model for this volatility. So now let me see here. So here you see that you have the z. So this z is going to be your random number. So let's check here. So you have your 1000 scenarios here for the next. So on scenario 1, this is how the volatility is going to behave over the next 50 days. So you see in here, well, I go and use this random numbers A1. And then in this one, I'm going to use random numbers B1. And so on and so forth. So now I have my volatilities for every single day. Now the third thing I need to do is I have to create returns. So returns are going to be created based on this formula. So based on this formula, I create the returns. Here I come. Let me go here all the way to the left. So I create my returns for my whole period. Now these are daily returns, which means that at the end of 18 days and 50 days, then you're going to have two returns. So this is just the sum of, for example, 50-day return is the sum of all 50 days. And you do that for each one of the scenarios. So then you're going to have 1000 scenarios for the 18-day return and 1000 scenarios for the 50-day return. So basically now you can compute what the price is going to be 18 days later, given that the initial price was, let me see what it was, so it was 53.97. So given that initial price, 18 days later, the price is going to be 48 and 52 in scenario 1. Now, with these two prices, we have to price all this either puts or calls that expire in 18 days that have a strike 43. So for example, this option in particular is going to be, well, it decides whether it's a call or a put. So in this case it's a call, and then it's going to be the maximum of BH3, which is 43. Sorry, that's for puts, so it's going to be the maximum between 48 minus 43, which is going to be 5. And then we do the same thing for all scenarios. Let's continue with this one. So I'll explain first this column. Now in this one is taking the one that expires in day 18 days. So now given that I do that, I'm going to have now here 1000 possible prices for this call option. So then I'm going to compute here the average price. So here it says discounted. That's actually wrong. In reality, this is just the price. So the price of the first option is going to be that average. The price of the second option is going to be that average, and so on. So you have to do that for all your options. So in this case, we have, let's see, some count 55 options. You have to do that for the 55 options. And then let's go back to here, the price. So we retrieve this price from the spreadsheet there. So this is going to be BH1006. So we retrieve that one from BH1006. And then the discounted price is going to be that price, and then discounted given the time to maturity and the interest rate. Now, so far we haven't done anything, in the sense that this input are just inputs. So now we need to compute the price difference, which is going to be the market call price minus the discounted price. And then we do that for every single call or put, for every single option. And then at the end, we're going to have up here. At the end, we're going to have that average. In this case, I'm doing it with average. That average error. And then how are you going to get your parameters? Well, you get your parameters basically, well, you put some initial values, and then let's put this one here. Doesn't change much. Let's see if this one's change. I don't know whether they're not changing. Oh, because they should be in here. Okay, so when we put these ones, you see that the error does actually change. So now the error is bigger. So the optimal after you run solver is this one here. Actually, I have to undo several times because I damaged my initial value. So I think this is the one that's going to give you the 0.34. Alright, so let's put these values here. Okay, you get the 0.40 here. Let's put these ones. You get the 0.34. So this is actually the error. Alright, so these are the optimal parameters, and then you'll have to use solver to minimize this number given these parameters, given that you change these parameters. Now you see that here you're changing also the initial volatility. Now this is, if you're curious, these are all the ways of computing the error. This would be the absolute percent error, and this would be done with the QA function. Now you see that the parameters are not the same if you change the error function. Finally, in Q8, what we do is, what happens if we introduce a new option? So this option is going to expire in 31 days, and it has a strike of 40. And then under each model, you can go and price. Now, this is a very difficult option to price because of the strike. It's very out of the money. It's a put option and so on. So you see that actually the models give you pretty different values. So these ones are kind of consistent, but I mean, this one would tell you, okay, it's about 2 cents, whereas this one tells you 10 cents, and this one tells you like even less than 1 cent. So tons of difference, but that's what this model is, or these models are about. So you have to see, okay, which model do I actually trust, and then go with that.